Well, good morning, everyone. Today I would like to introduce you two speakers. We have guests from the Russian Federation, from St. Petersburg, beautiful city, and they are coming from the Russian State Hydrometeorological University, but they are also working at the Institute of Oceanology of the Russian Academy of Science, Shirshov. So in first place, so they are guests of us. They are coming here, visiting us through a project which is led by Miguel Bruno. And in first place, it will be Ekaterina Sofina, with whom we share some experience. We have the common boss, and we have suffered the same old school. She would talk about modeling of the surface and internal tides in the Barents Sea, which is a bit colder than this one. Dynamics and energetics and tidally induced diapycnal diffusion. So, Katja, as you wish.
Hola. The subject of my report, it's okay? Modeling of surface and internal tides in the Barents Sea. Few words about the region of investigation. Barents Sea is located on European part of shelf Arctic Ocean. The boundary lays on the Kola Peninsula, Novaya Zemlya Island, Spitsbergen Land, Franz Joseph Land, and Bear Island. On the west and north, the boundary are close to the edge of shelf. The depth varies in general from 100 to 350 meters, and there is a deep near the Atlantic Ocean where depths can reach more than 500 meters, and there is a Spitsbergen bank. The climate of the Barents Sea is controlled by influence of warm Atlantic water, and so it's anomaly warm for this latitude. In fact, it's never covered by ice, completely covered by ice. For example, have a look at the age of the drift ice in the summer period. There is only a small amount of ice in the north of the sea. The shore-fast ice is absent in the Barents Sea in summer. In our previous studies was found that only shore-fast ice can affect it to the tidal dynamics, not drift ice. So if we are modeling the summer period, we can consider ice-free case. The surface tide in Barents Sea was the subject of numerous studies, most of them based on two-dimensional tidal models. About the internal tides, we know much less. There are only two-dimensional in vertical plane model, and distribution of the internal tide characteristics observed by satellite data. And at last, we have no any estimation of tidally induced diapycnal mixing. So our aim was to simulate three-dimensional tidal M2 dynamics and energetics, and estimate the internal tidal waves induced diapycnal diffusion in the Barents Sea in summer period. We used the model QUADI4 it's three-dimensional finite element model with sigma coordinate in vertical. It's based on three-dimensional primitive momentum equations in hydrostatic and Boussinesq approximation. In vertical, we used KL turbulence closure scheme by Mallory Mada. In horizontal, Smagorinsky formula is used. For sea level, used the wave equation, the depth average continuous equation in wave form. About boundary condition. At the bottom, the parameterized by the bottom stress parameterized by quadratic resistance law with standard coefficient. At the open boundary, the tidal elevation of M2 harmonic taken from the two-dimensional high-resolution model. For other variables, I used radiation condition. I said that we consider ice-free case, and initial time, the vertical profile of buoyancy frequency taken from climate data and invariable in space. So it assumes that internal tidal waves, it assumes that we exclude the influence of wind and thermohaline forcings to the simulation, because only a main influence of thermohaline forcing and wind forcing depends to horizontal variability of temperature and salinity. The horizontal resolution of the finite element grid varies from 1.5 kilometers to 19 kilometers. In the vertical, there are 40 layers, and time step equals about 10 seconds. It's enough to resolve the internal waves because baroclinic Rossby radius of deformation 8 kilometers. We start from state of rest, and quasi-periodic regime is reached after 30 tidal cycles. Here you can see the tidal chart of M2 wave. We can see two counterclockwise amphidromic system, which known by observation data. The comparison with sea level observation data shows that for amplitude, root mean square error is 4.4 centimeters, for phase 5.7 degrees. Here you can see the ellipses of barotropic tidal velocity. In the major part of the sea, clockwise rotation, the amplification of velocity we can see on Spitsbergen Bank, entrance to the White Sea, Church Bay. We compare with our results, modern results, with observation, some characteristic of the ellipses. It's measure minor semi-axis, orientation, eccentricity, and sense of rotation. And we have a reasonable agreement. Internal tidal waves. When we can evaluate the intensity of generation of internal tidal waves, normally the relative topographic slopes are used. Relative topographic slopes is topographic slopes normalized by slopes of internal tidal waves characteristics. But the main feature of internal waves in the Arctic Ocean is that they are trapped waves. For example, for internal tidal waves M2, the critical latitude is 75 degrees, where the tidal and inertial frequency are the same. So the slopes of internal tidal wave characteristic equals 0. On the other hand, to find the generation sides of internal tidal waves, use the average horizontal wave transport. If horizontal wave transport is orthogonal to the isabet, we can weight the generation side. But in the Barents Sea, this condition fulfilled on almost everywhere. At last, another indicator of the generation side is the density of baroclinic tidal energy. It's interesting that maximum values of predicted baroclinic tidal energy is coincide with the areas where internal tide are most often observed by satellite data. But predicted internal waves is low mode waves. Surface roughness is determined by high mode internal waves. This correlation can be explained the trapped waves, trapped nature of the internal waves. So the generation and dissipation of internal tidal waves happen locally, and low mode and high mode internal waves should locate it closely or even coincide with each other. Here you can see the equation for group velocity is from a linear theory of internal gravity waves. And if the frequency of tide and inertia are the same, the group velocity equals 0. So we can say that satellite data justified our predicted generation side. Internal tidal waves amplitudes. This is the distribution at the depth of 50 meters, the diapycnal depth. The maximum values is more than 15 meters on Spitsbergen Bank and near the Victoria Island. And on the southwest part of the sea, it's about 5–10 meters. In the remaining part of the Barents Sea, the amplitudes are less than 2 meters. Here you can see the cross-section of the generation site near the Victoria Island and on the Spitsbergen Bank. The maximum values of amplitudes are located on the crest of the bottom irregularity and in the slope. The internal tidal wave decay scale less than 50 kilometers. The reason of it is trapped waves. It's the trapped nature of internal waves. And the last item of my report, it's tidally induced diapycnal diffusion. It's known that tidally induced baroclinic tidal energy dissipate and induce the diapycnal diffusion. And so diapycnal diffusion can induce the change of temperature salinity much more tidal periods, the changes of much more tidal periods. So if we have the estimation of tidally induced diapycnal diffusion, we can answer to the question how strong the tide influence to the climate state. Here you can see the depth integrated dissipation of baroclinic tidal energy. It's controlled, in general, it's controlled the wave transport and bottom topography. To estimate the diapycnal diffusivity, we use Osborn formula. It's proportional to diapycnal diffusion or dissipation and inverse to the buoyancy frequency. Here you can see the vertical profile of diapycnal diffusivity in random points with different depths and the depth average field. The maximum values can reach 10 to the minus 1 in some region. And the average over the sea volume tidal induced diapycnal diffusivity equals to 5 times 10 to the minus 4 meters square per second, and we can compare it with estimate of vertical eddy diffusivity in the Barents Sea, determined by wind and thermohalide forcing. So we can say that tide have scientific effect to the climate in the Barents Sea. Here you can see the most important results. Of course, you can read them. We have the reasonable agreement with the data. Generation site I discovered but budget components of barotropical and baroclinic tidal energy, and these predicted generation site coincide with areas where are most often observed internal waves by SAR data. The extreme amplitudes can be internal tidal waves can be more than 20 meters, and in the remaining part of the Barents Sea are less than 2 meters. We can compare the coefficient of diapycnal mixing tidally induced and thermohaline and wind forcing. And so our conclusion that tidally induced diapycnal diffusion can make a contribution to the formation of the Barents Sea climate. If you are interested of my report, more detailed information you can find in this publication. Thank you very much for attention.
Thank you, Katja. I think that we time for I have one question.
Okay.
You have shown the results that the host patches of are located in the coastal, but also in the western open boundary of the Barents Sea.
Okay, this.
Yeah. Well, they clearly make a contribution to the local climate of the Barents Sea, but do you think that they can have also an influence further to the northern seas? Quite an impact on the global climate.
Yeah.
The problem of the deep water formation.
Exactly. In fact, when we choose a domain, we think about the geographical, but now we know that generations spots around the Spitsbergen island, and of course we consider much more domain to evaluate it.
Sorry, since I have problems with the microphone, but I will do it better in the laboratory. Well, thank you very much, Katja. If there are no more questions, then we can go to our next guest. Of the Oceanology. He's involved also with other topics, with some of the so he will show some developments related to the ocean atmosphere. Environments in the Baltic Sea there also.
Okay, thank you. Hello, everybody. Can you hear me? Okay. So, yes, I'm going to present you some results of our modeling activity concerning the Baltic Sea. And as it comes from the title of my presentation, we will be speaking about the challenges. But the main challenge is to model the Baltic Sea itself. It's really heavy and complex idea due to the nature of the basin. The major, let's say, key factors that do not simplify our life is it's a semi-enclosed basin connected to the ocean via the Danish Straits, and considerable river runoff from the mainly northern part, from strong density gradients and quite complex the circulation structure. For the many years of the investigation, from the data and from the modeling, our community had come to some understanding of the general principles of the circulation in the model, of the Baltic Sea, sorry. So the main driving force, of course, the permanent river runoff, and then forms the slope quasi-permanent slope from the north to the Danish Straits, which means the surface current prevalently goes to the southern direction, but it compensated by the deep circulation and compensation flow. And due to a very complex topography, there are a lot of interactions with the bathymetry, and we can expect also considerable vertical movement. Also, please know that it's quite shallow sea. The maximum depth, 400 meters, can be observed only here, just a small point, but mostly interested area for us, the deepest area called Gotland Deep, and the depth of it is about 250 meters. So the sea quite shallow. That means that the mixed layer in many layers hits the bottom, and also quite complex pattern of all the mixing processes appear through entire the basin. The main challenge for us to model this sea is to reproduce the salinity flow from the North Sea to the Baltic Sea. Here, for example, you have the time evolution of the salinity concentration on the Gotland Deep. Once more, I repeated it here. This plot comes from the data analysis, and we can observe that there are periods when there are no the inflow of the fresh salty water from the Northern Sea, but it also means that there is no refreshment of the near bottom area, and there appear anoxic conditions quite harmful for the ecosystem and for biology, mainly due to release of the nutrients and additional support to the eutrophication. So to really reproduce this type of movement in modeling approach, from the latest years we come to decision to join our efforts with our colleagues from several institutions, from Sweden, Swedish Meteorological Institute, Finnish Meteorological Institute, and our institution. Also, we have quite substantial support in scientific terms from the UK Met Office. They're also developing their model based on the NEMA code for the Shelf Sea. So the principle of our cooperation is to share the ideas, the code, and the configuration. We have a common configuration for entire the basin, but each team can also apply their specific research and specific configurations, and it's very easy to inherit or adopt the findings of your colleagues and to be concentrated on very specific topics and issues. That saves a lot of our efforts and time. Actually, our team mainly interested in the salinity and flow, and we're trying to reproduce it as much accurately as we can. From the scientific point of view, if we will try to look at the nature of the process, we can consider it like gravity-induced convection process when the heavy salty water comes from the North Sea. And then due to gravity acceleration, it tries to follow the slope of the topography, but the turbulence induced here make the release of and the dilution of the plume through the ocean interior. At this picture, of course, it's idealized experiment based on MIT GSM, quite heavy in time, and unfortunately, at the moment, we cannot propose non-hydrostatic solution for our evolution tasks and for operational tasks. So this is mainly idealistic to have the physical understanding of the process goes on. But actually in NEMA model, which is quite standard in terms of its z-coordinated and hydrostatic, it means that we've got the layers flow, and it's really challenge and hard task to reproduce these types of vertical movements. They cannot be explicitly solved in frame of the NEMA, and we need to parameterize it. So the major parameterization to reproduce these processes to use is a neutral diffusion. It means that our diffusion operators there works mainly along the diapycnal. It's also time consuming, but let us to, let's see, next. Okay. Let us to avoid the tendency when the dense water tries to jump out from the slope to the ocean interior, but we are trying to make it to follow the bottom topography and go to the Gotland Deep, since it's according to the nature, as we know from the data. And also we need to use the bottom parameterization, bottom layer parameterization. And in simple words, I'll try to explain how it works when the dense water comes and see there is a steep topography. There is no connection between these cells in normal, let's say, representation or vertical discretization, but the bottom parameterization makes the additional either advective or diffusion. It's up to the option which is mixing between those not connected cells. So it speeds up the movement of the dense water following the topography and help us to prevent the plume from its dilution. Yeah. Now we can see the exact result of the NEMA performance for this issue. The chart presents the 1-year simulation in 1993 or 63. There was some inflow event, and we can observe its development, how it tries to reach the Gotland Deep. Yeah. Without any parameterizations, normally the tendency of this plume would be to go directly, jump directly to the ocean interior. But just let's wait for a few seconds. You can see that due to diapycnal diffusion, it goes to the bottom. And also the key problem of all the models around the Baltic Sea is to predict the near bottom salinity. They are normally underestimated and by 2 per mile, something like this. And we did some progress in this direction, but at the moment we're exactly this simulation not yet happy with obtained results. And why? Because there are also quite complex processes that our model used to iterate with. And one of them is so-called Ekman pump motion. I'll try to explain it. So we can see it from the model. There is a vertical movement caused mainly by the eddy circulation formed by the cyclonic activity at the area of interest. So if we have a cyclonic activity, then the divergence of the velocity field causes the upwelling. In our terms, we have the diapycnal movement to a movement up, and it dilutes our plume coming to the bottom. Well, the process also well known, and there are a lot of data confirming it, either from satellites, altimetry, and the measurements, also with the models. But again, due to hydrostatic assumption, we are not sure how we will can reproduce it in our model, and some tuning we need to apply here, and the mechanism by which we can affect it is to use the Williams parameterization proposed previously. And the idea of this parameterization is to locally increase the velocity if we can see that there is a budget of available potential energy, or where we have the slope of the density changing with that coordinate. So this added term, velocity field, not divergent, and we can obtain it from the constant coefficient multiplied by the slope, but depending on its change via the water column. Here you can compare the performance of the model. On the left, there is known parameter AD induced velocity used, but here you can see how it performs. Absolutely unlinear effect, maybe unexpected, but the local increase in the later diffusion and advection lead us to preserve the plume. You see? And actually let us increase the near bottom salinity in our target area. Sorry, there's not enough colors to outline those two pictures on a beamer, but on a screen, so the difference will be for near bottom salinity about 1 per mile here between those two pictures. Another topic that we're interested in to evaluate is the representation of convection, also in frame of the non-hydrostatic approach, And let's consider the upwelling events. We have a fine resolution model also for the Gulf of Finland based on the same code. The effective resolution is 500 meters. Here we can see the satellite SST estimation from the MODIS. If we have 3 or 4 days along shore wind from the east to west, we can observe substantial upwelling events in our basin. That also quite important factor of the nutrients input to the mixed layer, but also change the stratification of the mixed layer and something quite substantially. So if we'll cross-sect this event like here in the model, I'll try to explain you our experiment. We are first switched off all the vertical mixing, just set it to the molecular background value. And due to this fun experiment, we can observe so-called the shear induced convection, since we have the major movement from the south to the north by upwelling. Salty water comes up and then overlies more lighter water. So we have instability here, and this is topic to be resolved somehow in hydrostatic approach by some either adjustment schemes, for example, like this. It's simply locally increase the vertical mixing coefficient, or we perform a lot of tests with different schemes, vertical turbulence schemes available in the model, and it's also advantage of the model since we can easily switch between the different blocks and test a lot of vertical closure schemes. Here I represent the results where the TKE and GLS in comparison performs when they can note the instability in the water column, and we can see that the general normal mixing scheme if they have the energy evaluation equation or length scale evaluation equation, they can see the instability and can also locally increase the coefficient and to restratify the upper mixed layer. So the event quite substantial. And from our previous model and our colleagues' model experiments, we know that normally models, they do underestimate the mixing depth. Keep it. What we're also trying to evaluate is the effective resolution that we actually need. And here we can see the difference of 2-kilometer model resolution with 500 meters and the satellite. So we can see more developed frontal structure on the final resolution. That means that at least a substantial part of the AD dynamics is trapped by the model. But if you have a look at the general performance of different realizations, we can see that it is quite okay. The chart presents our summer cruise, so each set of the profiles. It's an average for the eastern, central, and western part of the Gulf of Finland, about 20 or 30 profiles averaged with standard deviation. And we can see that both of the resolutions, they follow the general tendency, and the main tendency is that at the western part we have more pronounced, more deeper mixed layer, but it's sharp, quite sharp, but also deep in the central part and very shallow in the eastern. So the previous understanding was that it's because of the stratification changed and the vertical mixing can penetrate deeper in the western part of the Gulf of Finland. But according to our experiments and results, let me explain you what I have here. We are trying to subdivide these physical processes by plotting the depths of the wind mixing can penetrate. We know it from the depths of the turbocline. Turbocline we define as the depths of the mixing coefficient when it's different from the background. So this actually to the maximum depths where we can penetrate, where the wind-induced mixing can penetrate. And we have it for the May and for the June-August periods maximum. We can see that during the upwelling that I have shown you previously, the major of wind mixing appear. And for the rest of the period, there is no any substantial mixing activity. But at the same time, if you will follow the development of the bottom thermocline, in the May, it's formed mainly by these mixing activities, but during the rest of the summer, we can see that it's deeper and deeper and do not connect with any wind activity. So our conclusion that it's mainly the boundary processes, and we import the warm, salty water from the Baltic. We also have now working to confirm it with fine resolution data comes from our colleagues from Estonia. They have a buoy station over here. And if here we compare two different resolutions of our models, we can see that the finer model and with AD dynamic, they reflect the general tendency of the submesoscale activity in the entrance of the Gulf of Finland. You see the tendency of the mixed layer evolution. But the more crowd model, well, performs not so well. Okay, and then just a few about the technical realization of the model. Of course, we need to use quite heavy computation power for it. And for example, for our evaluation tasks, I'm showing you our estimations for the, let's say, moderate number of processors. We can afford 1 month of simulation to get the solution for 50 years with a resolution 500 meters for entire Gulf of Finland. So the model suits well for climatic research. It's still quite far to explicitly resolve a lot of processes that have critical importance, but at least a part of them we can successfully parameterize, as I showed you. At what we are now working on is to have more advanced horizontal discretization, to have the condensed areas where we've got specific interests, like let's say the Danish Straits and the Gulf of Finland. Some new physics comes with the new versions of the NEMA 3.6, but I would say that for several years this modeling technique will keep us busy. But in some future I can assume and can predict that we have to also skip to the non-hydrostatic approach and try to represent all the physical activity more accurately. So here there's a lot of space for cooperation. That's why we're here. We're also working with these issues. And this is, let's say, my brief overview of our activity. And thank you. And please, questions?
Thank you very much, Roman. And now again, is there any question about, please, Carlos?
Hi. Is there any reason for not using a sigma coordinate model in the vertical? And do you think it would be a significant difference about the bottom transport you commented at the first part of your speech?
Okay. The main reason, as we know from the previous modeling studies, that for the shallow, when you have a considerable slope, so in the sigma coordinated model, you have a lot of artificial mixing. So historically, we used the Z-coordinated model. But now, there are a lot of options to have hybrid systems. Sigma Z-coordinated hybrid system. When it's quite complex, but already implemented in NEMA, and maybe for the next year we will try to use it. And of course, you're right. That some advantage of it is to more accurately reproduce the plume movement. But the interaction with topography is still the question. But we believe that the hybrid system can solve it partly. Yeah.
Thank you. More questions? I have one question. Did you check how accurate it's your plume development depending on the vertical resolution? So how much the numerical vertical diffusivity impacts on the solution you're obtaining when you're using your, I think it was 97 and 49 vertical
You're asking
layers.
about the Baltic.
Yeah.
Not the GAN, because in the GAN for
no, the Baltic, the inflow
1
of the
meter,
Atlantic water.
also inflow, 1 meter resolution. But for the Baltic, we have about 2 meters also vertical resolution, extremely high. And well, of course, at some future experiments, maybe we will reduce it. But
yeah, but you have not made tests, for example, using 4 meter resolutions. How?
No, we just take the best one to be sure that
maximum.
They're the maximum.
Okay, thank you very much. Any other question? So, we thank both our speakers, Ekaterina Sofina and Roman Vankevich, for being here today with us. Thank you very much.
Thank you.